Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second in a series of 3 videos on understanding capacitance. In the first video, I answered the questions, what is a capacitor? How is it built? And how does it work? In this video, I want to provide you with the most common and needed equations that relate to the use of capacitors in design. I am also going to introduce you to the model of real-life capacitors with a brief explanation of the limitations it places on capacitor usage. So let's dive into this design stuff. And so now we're going to talk about design-related stuff. And right at the very beginning, we want to talk about series and parallel capacitors. In order to better understand series and parallel capacitors, we have to remind ourselves just a little bit about how they're made. Remember, we have 2 conductive plates, and they're separated from one another by an insulating material of some flavor. They're a distance apart. They have a particular area. The larger the area of the conductive surfaces, the larger the capacitance. The further away you take those plates, the less the capacitance. And so now let's take a look at the equations for parallel capacitors. Okay, so now we have capacitors in parallel with one another. Now it's kind of easy to see. Parallel capacitors are probably the easiest ones to understand because we have this area here connected to this area here, connected to this area here, and the same thing on the bottom. Each of the areas of the other plates are connected together. So it's kind of intuitively obvious that essentially we have this area plus this area plus this area, and when the area of the conductive plates increases, then the capacitance increases. So it turns out when you have parallel capacitors that the total capacitance is equal to the capacitance of each capacitor added together. Now they're all connected together. This is a conductor. Is it possible for these to be at different voltages? Well, no, because they're all connected together with conductors. So the voltage on this capacitor equals the voltage on this capacitor equals the voltage on this capacitor. So total capacitance equals C1 plus C2 plus C3 plus C4 plus on infinitum, as many capacitors as you put in parallel. And the voltage on each capacitor is the same as the voltage on every other capacitor. Now what's a little more difficult to understand is when we start talking about series capacitors, and that's what I'm going to be doing in the very next section here. Series capacitance gets a little hairier, but just to begin with, what happens when we put them together? How do we calculate the total capacitance of a series of capacitors? Well, let's just think about the physical situation here. We have this capacitor here in series with this capacitor, in series with this capacitor. This capacitor has a certain area, this capacitor a certain area, this capacitor a certain area, and there's a distance between their conductive surfaces D1, D2, and D3. So we can kind of think like when we put capacitors in series, we're kind of stacking these insulating materials together, creating a distance between our 2 conductive plates that is the addition of those 3 distances between the plates over here. So it makes sense the capacitance of a series of capacitors put together is lower than the smallest capacitor that is here. And the equation for this is very similar to resistors in parallel. In fact, it's the exact same formula, only with capacitors and capacitors in series. So the total capacitance is equal to 1 divided by 1 over C1 plus 1 over C2 plus 1 over C3 plus 1 over as many as you have. But if you only have 2 capacitors in series, then it's a lot simpler, just like with resistors. The total capacitance is equal to the product of the 2 capacitances divided by the sum of the 2 capacitances. And if they happen to be equal value, then it's even simpler. If you have 3 30 picofarad capacitors in series, then the total is 10 picofarads. Now, what happens with the voltage that's applied across this? Well, it's distributed across all of the capacitors. And without going into all of the derivation, remember that capacitance is charge per volt. And that very reality is going to come into deriving the equation that we're going to be using here. It turns out that it's distributed on the basis of the value of the capacitor, but not quite the way you might think. The voltage across any particular capacitor in a string of series capacitors is going to be equal to the applied voltage across the entire capacitor string times this quantity, which is this total capacitance that we just calculated up here, divided by the value of the particular capacitor. So that means that if this is a 10 microfarad capacitor and this is a 30 microfarad capacitor, then the voltage across this 30 microfarad capacitor is going to be lower, because it's a bigger value down here, it's going to be lower than it is across the 10 microfarad capacitor. So when you put capacitors in series like this, you have to be mindful of the voltage rating of the particular capacitor you're using and how this plays out in the voltage that appears across in the individual capacitors in our series. So, now let's dive into some more dynamic stuff. And we're going to begin with talking about the time domain. When we think about the time domain, this is where we live. One thing comes after another. We watch as a bird flies from here to there. We see the blinking of a light and we see, a regular time to it. We connect a meter to the output of a power supply and turn on the switch, and we watch that output voltage come up until it comes up to its output voltage. All of these things are things that occur as time progresses. We experience life as we sense things changing over time. Now, a capacitor charging is not an instantaneous process. Just like filling that tank is not an instantaneous process. We open the valve on the tank and it takes time for the fluid to flow into the tank and for it to finally come to a place of equilibrium. In the same sense, we're filling this capacitor with charge, and that takes a finite amount of time. Now, if we add a current limiting resistor, essentially taking that input valve on our tank and throttling it back so it can't supply as much fluid, as much flow of fluid into the tank as it might otherwise do, then we can slow down that process, and we watch the voltage across the capacitor. We can actually watch as that tank fills, as the capacitor fills with charge. Now, you will notice that that this is not a linear process, just like filling the tank is not a linear process. This is not a linear process. So if we have time going here, and we have voltage going here, you're going to see it looks just like that. And so we get a lot of charge really quickly into the capacitor right out of the gate. And if we were to take the resistance in ohms and multiply it times the capacitance in farads, we get what's called the RC time constant of this circuit. RC time constant. And you say, well, what does that tell me? This RC time constant is in seconds. So if we were to look at this charging curve and go up here until we are at the 63% mark. So if this is 10 volts, let's say, for fully charged, this would be 6.3 volts. It takes one time constant, to charge that capacitor to 63% of the applied voltage here. Now that leaves us with about 37% between here and here. In the next time constant, so this is time constant number 2, we are going to charge that capacitor to 63% of this remaining 37%. So we will now be at 86% of full charge. And then in the next time constant, now at 86%, what does that leave us? It leaves us 14% left before we get to the full charge. In the next time constant, we're going to charge it an additional 63% of the remaining 14%. So it keeps doing that. Well, if you do the math, you realize that technically it never actually reaches the applied voltage. It gets really close. In this third time constant, we are now at 95%. And then you have the fourth and the fifth and the sixth time constant. So there is a formula that you can use to calculate what is the voltage across this capacitor at any specific time t, if you know what the resistor is and the capacitor is and the applied voltage. And this is the equation. And so we have the voltage across the capacitor, that's this one, is equal to the applied voltage, that is this voltage right over here, times this quantity, which is 1, minus, and you go, what on earth is this thing? Don't let it scare you. You look at your scientific calculator, you're going to find this. This is Euler's number, which is about 2.715, as I recall. Okay, so this is Euler's number. It's spelled E-U-L-E-R, Euler's number, and it's raised to this power, minus t, that's the time that you're interested in, divided by this RC time constant. So you take this resistance in ohms, multiply it by this capacitance in farads, you divide it into the time that you're interested in figuring out what that voltage is. You put a minus sign in front of that, and using your scientific calculator, you raise Euler's number to that power. You subtract it from 1, you multiply it times your applied voltage, and you get the voltage across this capacitor. So this is the equation for voltage across the capacitor at any given time t in seconds with a resistor of size R ohms and capacitor in farads. Now, to find the time at which a capacitor will charge to a specific voltage, you need to use this equation. And so to get the time in seconds, you need to use this equation. Oh, this looks weird, doesn't it? Well, you have a negative sign out in front here because you can't have negative time, and this comes out as a negative number. It's the resistance in ohms times the capacitance in farads. And you say, what is this? This is called the natural logarithm. The natural logarithm is answering the question, what is, if this is the number, the natural logarithm of this number is equal to the power that I raise Euler's number to get this number. And again, if you have a scientific calculator, that's there. So you don't have to know much except use your scientific calculator. So it's the natural logarithm of this quantity, which is 1 minus the voltage across the capacitor divided by the voltage applied. So first you take this, you multiply the voltage across the capacitor that you're interested in by the applied voltage. You subtract that from 1 using your scientific calculator. You take the natural logarithm of that, multiply it times the resistance in ohms, times the capacitance in farads, and that will give you the time in seconds, that it will take this circuit for the voltage across the capacitor to reach a specific level. Well, what if you have a particular capacitor, a particular resistor, and you know that either the resistor or the capacitor, and you know the voltage that you're applying, but you want the voltage across that capacitor to be a particular voltage by a specific time. Well, I'm going to just throw these equations up on the board for you, but all of these equations are going to be in the comments or available to you with this video posting. So here are the equations that you need for those two particular scenarios. And so here are the two companion equations. If you know your capacitor, you know the time, you know the voltage that you want on the capacitor, and you know the voltage applied, then the resistance necessary to make this happen, again the minus sign because you can't have minus resistance, is equal to the capacitor value in farads divided by the time in question in seconds times the natural log of this quantity, 1 minus the capacitor voltage that you're interested in divided by the applied voltage. And the only difference between these two is that the R and C switch positions when you know the resistor and want to calculate the capacitor. And so these are the companion equations to the first one. And now we're going to go on to capacitive reactance and the frequency domain. When we're talking about design-related stuff, you can't escape the frequency domain. It's a very important portion of the use of capacitors in the frequency domain because this is the place where we design filters and oscillators and antenna traps and tuned circuits and anything that is frequency related. This is the view of the world where our concern is how things happen and how things respond with regard to frequency as opposed to time. Now, in that world of the frequency domain, we have impedance. Impedance is kind of like the generic all-encompassing entity, which is like resistance with resistors, but they incorporate these reactive components like capacitors. Now, capacitive reactance is like AC resistance, only it refers to capacitors. It uses one of those really weird, inescapable numbers that you just, this right here, weird yet inescapable number, J, which is the square root of -1. Now, if you look at my video on weird numbers in electronics, I will explain why this is impossible. It's an impossible number because you can't take the square root of a negative number. But yet there it is, and it's part of this, and you can't escape it. So this is the equation for capacitive reactance, the equation for calculating the impedance of a capacitor. And it is -J, that's our weird, inescapable number here, divided by this quantity in the bottom, which is 2 times pi times the frequency in hertz times the capacitance in farads. And this has the units, believe it or not, of ohms. So capacitive reactance has the unit of ohms. Now, I pointed out to you already that there's a -J on top. This is the weird yet inescapable number. Well, I don't want to go into a lot of the details, but for sake of completeness, I have to mention this. When we are plotting impedance, there is the real part. So we have a set of axes like this. And normally, if you've done any math at all, you know that this is the x-axis, and to the right is the positive x-axis, and this is the y-axis, and this is the positive y-axis, and this is the minus y-axis. Over here is the minus x-axis. And this is the normal Cartesian coordinates, as they're called. Well, when we're talking about impedance, we are talking about this weirdness here. We have the imaginary plane, and instead of this being the x-axis, this is the real axis, and this is the imaginary axis. And because this has a -J on top, this is the -J axis down here, plus J, because we have this -J on top, that means that when we plot the impedance of a capacitor on these coordinates here, we plot it on the negative J axis down here. Resistors are all real. So resistors are out here. Capacitors are down here on the negative axis. So I will be covering this whole business here and dealing with this in a future video that I'm planning on phasers. No, we're not talking about Star Trek. We're talking about phasers as in this stuff. This is a phaser. The last thing I want to talk about is just a brief moment on the phase aspect of capacitors. And this is a little harder to grasp, and it affects our use of capacitors both in the time and the frequency domain. They say that the phase of the voltage across the capacitor always lags the phase of the current into the capacitor. And that makes sense, because if you think about it, you have a capacitor with no charge on it. And when you first turn on the switch and start chunking charge into it, the capacitor acts like a short and just sucks every bit of charge it can get. The current goes way up real fast. Meanwhile, the voltage just kind of meanders its way up. And as the voltage begins to reach its peak, just about then, the current reaches its minimum. And vice versa. And so it makes sense when you think about the filling of the tank and how fast the fluid goes into the tank and the level of the fluid in the tank. It makes sense that we would say that the voltage lags the current by some value, and they say 90 degrees is that value. Now that we've considered the ideal capacitor and all of the theories that make it work, we have to consider the real capacitor. The capacitors we use in real life and practice do not always act like capacitors. Now, here are some foundational facts that we have to remember. Every conductor, no matter how short or how small, has both resistance and inductance. No insulators are perfect. So these very facts all add up to something that is less than the ideal capacitor. And so we have this capacitor model. We have a resistor in series with an inductor in series with this parallel combination of our ideal capacitor and some resistance over here that I've just labeled leakage. This up here is the ESR, or equivalent series resistance. And the equivalent series resistance is the sum of the ohmic losses of the dielectric, the materials that are used, the connections used in the construction of the capacitor. Unfortunately, not all data sheets will tell you what this is, and the reason is that when you're talking about frequency-related stuff, it's not a fixed value. It's actually a frequency-dependent value. So they might say low ESR and then never tell you what it is. Instead, what they might tell you is, well, here's the dissipation factor of this capacitor. And you go, well, okay, what's the dissipation factor? Well, it's real easy. When it comes to the equivalent series resistance, the dissipation factor, ESR, is equal to the dissipation factor, I'm just going to abbreviate it this way, the dissipation factor that they give you on the data sheet times the inductive reactance of the ideal capacitor. So you take, if you're interested in the ESR of your capacitor, you need they'll either give it to you on the data sheet or you find the dissipation factor and then do this math to figure out what the ESR is at a particular frequency. Next is the equivalent series inductance, which is this inductor that we've stuck in here. And like I said, all connections, all wires, all conductors have a certain amount of inductance associated with it. And then we have the leakage down here. You ever charge up a capacitor and then wonder why it discharges all by itself? That's this guy right here. Now, the ESR, let's just talk about how this affects your design and talking about ESR? Well, it lengthens the charging time of the capacitor, as you can probably guess. Just like any RC time constant, it's going to lengthen the charge time. It bears the brunt of repeated sudden charging cycle, like connecting a connector on and off. I once worked for a medical company. We had a wearable EEG amplifier that you would wear on your hip. This is for people with epilepsy, and they had to monitor them, and they have the cord. And we had a little bit of a problem. You know, we would connect and disconnect this cable, hot connecting, because it was coming from a power supply over here, and this capacitor would just go pop, big flashlight, smelly stuff. Well, it turned out it was the ESR of that capacitor right on the inlet that just couldn't take that pounding. If you just sat there and went like this, it would eventually pop because it would get too hot and lose its mind. Well, we fixed that, obviously, but you have to take that into consideration. It reduces the voltage at the terminals when we draw current. You have a series resistor. It has a voltage drop across the resistor when you draw current through it. So obviously, when you're drawing current from the capacitor, your ESR is going to limit the voltage that you can get from the capacitor itself. It reduces the Q of the capacitor. And this is another strange thing out there, Q. Q has to do with how well a capacitor or a tuned circuit will tune very sharply. And ESR is the guy that kills that. You say, well, what is Q? Well, Q for any particular device is equal to the capacitive reactance divided by the ESR. So you take your capacitive reactance of this ideal capacitor, you divide it by the ESR of this at that particular frequency, and you get the Q at the frequency that you're interested in. And so Q is equal to the capacitive reactance divided by the ESR of the capacitor. All right, let's talk about the ESL, the equivalent series inductance. Well, you know, at some point in time, remember resonance, and we haven't gotten here in the whole series of videos, because I haven't talked about inductance yet and resonant circuits. But when the inductive reactance and the capacitive reactance become equal, you are said to have a resonant circuit. And it turns out that at that particular moment in time, for a series resonant circuit like this, all of a sudden the capacitor and the inductor disappear. They're not, you don't see a capacitor, you don't see an inductor, it just disappears. And as frequency increases, and again we haven't gotten here yet, X sub C, this capacitive reactance, goes down as we increase frequency. So the higher the frequency, the lower this value is. And as we go up in frequency, the higher the inductive reactance is. They act in opposite directions. So once you pass that place of resonance where they're equal, all of a sudden your capacitor looks like an inductor. It doesn't look like a capacitor anymore. Plus, inductors get in the way of fast changing currents because they oppose the change in current in a similar way that capacitors oppose the change in voltage on them. And then last we'll talk about leakage. Leakage. The real capacitor never actually draws no current. A real capacitor will self-discharge over time. Now don't count on that. You charge up a high voltage capacitor and then walk away. Don't assume that it's discharged when you get back to it, because it might be discharging a lot more slowly than you expect. Never take that chance. but it will discharge over time. So what happens? Well, the problem is, remember we were talking about how you have series capacitance? Okay? Reality is inside of this capacitor are these leakage currents that are there. And you could have two capacitors come off the manufacturing line, one right after the other. They could be equal values of capacitance. And everything is supposed to be equal. But when you apply your battery voltage to this thing, you'll find that this voltage is going to be different than this voltage, is going to be different than this voltage, because the value of these leakage resistors, these leakage currents inside that capacitor, are not equal between the capacitors, even if they're right off the same manufacturing line. So what you end up having to do to overcome this here is you have to add your own external purposeful bunch of resistors out here. And let's just say if this is 1 microamp maximum leakage through this capacitor, and they're all the same, so the data sheet says 1 microamp of leakage current through the capacitor, then what you want is you want current through this to be at least 10 microamps. So you are swamping out whatever differences that there might be, because the data sheet might say 1 microamp for all these capacitors, but this might be 0.5 microamps. And this one might be 0.75 microamps. And this one could be 0.85 microamps. And if we don't have this over here, then because each one wants to leak at a different rate, the voltage across each capacitor isn't going to follow that nice rule that we had before, because we have a real capacitor with real leakage in it. And so you have to add these external resistors to it. Now, what about the impedance of the capacitor? We have to consider what the impedance of the capacitor might be. So what is the impedance of a capacitor? Well, ideally, the impedance of a capacitor is the capacitive reactance of the capacitor, which we've already learned is minus J over 2 pi times the frequency in hertz times the capacitance in farads. But in real life, we have all of this other stuff in here. We have the ESR and the ESL to deal with. So the reality is the impedance of the capacitor is this equation here, ESR plus J times the difference between the inductive reactance and the capacitive reactance. Now, in most cases, this is all we need. So we don't have to pay attention to this stuff down here unless we're getting into some really picky electronics and RF stuff and things like that. For the most part, and in lower frequencies and the like, this is just fine. But if you really want to get picky about it, you have to go the next step. And then the magnitude of the impedance is this mess down here. So there you have it with real life capacitors and everything that goes with it. Now I'm going to show you a quick little demonstration to show you that this is the case, that this does look like this. And I'll be doing it on my vector network analyzer.
All right, so here is a very standard ceramic 330 picofarad capacitor, and I'm going to put this on the vector network analyzer and we're going to see what happens to it as we increase frequency. So what we're looking at here is the phase of the impedance of the capacitor, and you would expect, because there's a minus J on the top of that capacitive reactance, that the phase is going to be negative, 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 negative. But just take a look right here. What happens here? It goes from negative to positive. So right at this particular point, right here, the capacitor goes from being a capacitor to being an inductor. So the long and the short of it is, this little 330 picofarad capacitor went from being a capacitor to an inductor at around 119 megahertz. So you need to be mindful when you're going up in frequency, is my capacitor really a capacitor?
So there you have it, the design-related stuff. Well, I'm done with the second video in the series. If you're interested in some more of the nuts and bolts of why things work the way they work, be sure to watch the extra credit video. In the meanwhile, thanks for watching. Toodaloots.